Last lecture we had seen the following. We had so our goal was to build a very simple op-amp with a gain of 1000 with an input resistance of 100K and an output resistance of 100 ohms. So we started off with a very simple differential pair here that you see. And just to keep it simple, we had avoided a current mirror load here, which would have required us to use PNP transistors as well. And that makes it a little bit more difficult to implement in a lab. So I'll show you the results for this particular op-amp that some students had taken and implemented it in the lab, and the performance of that particular op-amp here. So anyway, so we took this, we looked at this differential pair, and what we did was we designed this differential pair with the aim of satisfying first the input resistance here, because it's a multi-stage amplifier. The burden of satisfying the input resistance is on the differential pair. That's the first stage here. And on that basis, we had arrived at a current of 0.1 milliampere, which allows us to get a differential input resistance of larger than or about 100K here. And then what we had done was design this differential pair such that it gives us the maximum gain. And with that objective, we had found that maximum gain requires that the drop across this particular resistor should be as large as possible. And therefore, we had pushed this voltage to very low value. So VCE, we had chosen it to be equal to 1 volt here. And on that basis, we had obtained a differential pair, which gives us a gain of 227. Obviously not enough for a gain of 1000. And therefore, we have to use a second gain stage. And for that, we had used a common emitter amplifier. And we had looked at the common emitter amplifier, and we had found that in this configuration, this amplifier doesn't give you any gain. Doesn't give you any gain because the gain of this particular stage is the drop across the collector divided by the drop across the emitter, and the two drops are comparable in nature, and you get a gain equal to 1 or less. And no matter what you do to the biasing here, the gain of this particular stage would remain less than 1 here. So then what we had done was we had said that don't look at a NPN gain stage, look at a PNP gain stage here. A PNP gain stage, and to complete the op-amp, we had said that you have to add a common collector amplifier to, to provide the lower output resistance here. So that was a very simple op-amp, and what we had seen was that if you design this differential pair with the maximum possible gain, and then you look at the design of this common emitter amplifier, you find that again you don't get any gain. You don't get any gain, and therefore what we had to do was reduce the gain of this particular stage, and which allows us to increase the gain here. And you have to do a balancing act, decrease here and increase here. And if you do that, properly, you can get a gain which is close to 1000. So you can get a gain close to 1000. But the problem with this particular stage was that the output resistance looking from here was large because we had to use a large resistor here. And we had to use a large resistor here because we want a reasonable resistor, large resistor here, because the input resistance, when you look from here, should not load the previous stage here. So that requires that this resistor be large, and then the ratio of these two resistors gives us the gain. So this resistor becomes large, and that causes the output resistance to become high also. So it satisfies, it's close to the specs that we want in terms of gain and input resistance, but output resistance is too high. So then we said that maybe one can look at a Darlington pair here, and with the Darlington pair, one can obviously, you can see here output resistance becomes very low. But what happens is when you use a Darlington pair here, one has to look at the biasing as well. And so when you adjust the biasing, you find that you can't use 160K here, you can only use 80K, and the gain reduces here. Of course, you can do something else also. You can go ahead and re-look at the design of differential pair and this particular stage and try to push the gain up. But what we did was we looked at another approach that this particular stage has high output resistance because this resistor is high. And we said this resistor is high because I want this resistor to be reasonable to avoid the loading of the previous stage here. So one way of avoiding the whole thing is what you do is you add another stage, a common collector stage here, which prevents the loading of differential pair by the gain stage here. And then this allows you to reduce this particular resistor. From 160K, you can get it to 9K. Note that we reduce this resistor and we reduce this resistor as well. And therefore, we can get a large gain as a ratio of these two, but use of a small resistor does not load the differential pair as well. So this use of a common collector stage allows us to reduce this particular resistor, therefore obtain a small output resistance, at the same time not load the previous stage, and we obtain a large gain also. Yes?
Can't we use a MOSFET so that loading does not happen?
Sure, you can use a MOSFET. Maybe you'll get a NSEM problem where a MOSFET and bipolar are combined together. We have seen one. You can do that. I'm deliberately keeping the op-amp simple so that, as I said, one can implement it relatively easily, maybe in 3-4 hours in a lab. So one of the objective was to keep it as simple as possible. There are many options in this. As I said, active stage, you can use a MOSFET. You can build the entire op-amp using MOSFETs. Sure. So we had arrived at this particular design. It's not that, as I said, there are many options open here. This is one particular design here. And with that, if you simulate, you find that you do get output resistance less than 100. You do get gain, which is a little larger than 1000. And input resistance, we had earlier satisfied a value of 100K. So this is the op-amp that you get, and if you simulate, you find that it works as expected. So this is our sort of final design. Okay, and then the design of the op-amp is not finished as yet. And the reason for this is as follows. So suppose I take my design, op-amp that I've designed, and I make a buffer out of it. And if I make a buffer out of it, of course, I'll connect the input and the output. And what we expect is that if you apply an input voltage, whatever input voltage you apply, you'll get the same output voltage here. So when I make a buffer, and so far I'm only showing you simulation results. When you make a buffer, even though you don't apply any input voltage, so this is the op-amp here. There's slight change here in terms of resistor here, but more or less the same. What happens is, if you simulate, the output shows oscillations. This is the case where you don't have, one has not applied any input, and the output is showing fairly large oscillations here. You can see initially there's the circuit takes some time to the oscillations are probably building up, and then eventually they reach a stage of, you can see here, +3 and -3. So even when you don't apply any input, this is a case where I applied a square wave. You can see here a square wave that this is the input here, and the output. Note that the output has all this thing there. So besides, you can see a sort of a square wave is there maybe, but along with that, what you have is large number of oscillations. So the reason for this is that your op-amp is unstable. The moment you take this op-amp and you put a feedback, it becomes unstable. And that's why I was saying that most op-amps, when you design and you put feedback, negative feedback, note that the feedback is negative, the op-amp will become unstable. And so what we have to do is, we have to look into the op-amp and see what is the source of this instability here. So one way of, that looking at instability is, you look at the open loop characteristics. So this shows you the open loop gain versus frequency. And I'm sure by now all of you know that one of the ways of characterizing instability or stability is gain margin, phase margin, right? So what we do is, we look at our op-amp, the op-amp that we have designed, and we look at its open loop characteristics, and we go to this frequency called unity gain frequency. At this unity gain frequency, where the gain of the op-amp becomes 0 dB, or which becomes equal to 1. So this frequency is 232 megahertz. Alright, so we go to this particular frequency, and at that frequency, we look at the phase, right? So I go ahead and look at the phase response, and phase response at that point is negative. So phase margin is actually negative of this particular op-amp. And you know that for reasonable op-amps or reasonable circuits, you require phase margin of at least larger than 45 degrees. In fact, even with 45 degrees, if you excite your op-amp, you'll get a lot of overshoots and undershoots and all that here. So if you want a fairly stable response, you want maybe phase margin of 75 degrees or 90 degrees. So the phase margin is actually negative. Now what we have to do is, we have to make phase margin positive, right? We have to make phase margin positive, and the way you do it is, the whole process is called compensation. So what we need to do is the following. Note that if I look at this particular diagram here, phase margin is negative, but if I go up in frequency, the phase margin obviously is positive, right? So suppose the open loop characteristics, the gain had gone to 1 at 10 megahertz. if my open loop gain had decreased to 1 or 0 dB at 10 megahertz, then I would have obtained a phase margin of 60 degrees. So what I need to do is, I need to alter the frequency response here. And the way we do it, I'm not going to go into the details because that's a feedback and compensation is a whole chapter by itself. So what we do is, we need to add a pole. We need to add a pole. I'll just show you what we need to do is, add a pole at some frequency which is lower. So there are obviously poles and zeros and all that which is causing this response to decrease, right? And phase to change. So what we are saying is, add a dominant pole, a pole at a lower frequency. What this pole will do, one single pole, will cause the gain to drop at 20 dB per decade. And then, let's say if you introduce it at a suitable this thing here, so this is the unity gain frequency now, and then you go ahead and look at the phase at this particular point. And if you do it suitably, if you introduce poles suitably, what you may find is that the phase at this particular point is now positive and of a reasonable magnitude. Okay, so that's the idea. The idea of making the op amp stable is to introduce a dominant pole at a suitable lower frequency here. Now, obviously, I can note that I can introduce a pole here. I could introduce a pole here. I could introduce a pole here. I could introduce it anywhere that I want. But there are consequences. And what are the consequences? If I introduce a pole here, note that my 3 dB or my unity gain frequency becomes here, maybe 8 megahertz here, right? Earlier, what was the unity gain frequency? 230 megahertz. So the price that you're paying for making the op amp stable is, you're losing the frequency response. You're losing the frequency response. Your op amp is going from a initial 230 megahertz to a maybe 8 megahertz. Now, let's say, suppose this gives you a phase margin. I'm just throwing a number. Suppose it gives you a phase margin of 45 degrees. You're not happy with 45 degree phase margin. You want 75. So what do you have to do? You have to take this pole and push it even to lower frequency. If you push it to even lower frequency, then it will go and intersect here somewhere. And when it intersects here at a lower frequency, you'll find the phase margin will increase. So you are seeing that there's a trade-off between stability, which measured in terms of phase margin, and the frequency response here in terms of unity gain frequency, right? So that's a trade-off that one has to carry out. But anyway, as I said, we need a phase margin of at least 45 degrees. Most op amps, you would require that much. Okay. So what we have to do is then, in our op amp, we have to introduce a dominant pole. Okay. So now how do I do that? Now note that if I'm introducing a dominant pole in my op amp, then if I'm introducing it somewhere here, then the frequency response can be modeled to the first order approximation entirely as a result of the dominant pole. The other poles are coming at higher frequencies here. Okay, so I'm going to approximate the frequency response in terms of one single pole right now. There are other poles, but they exist at higher frequency. Okay, so this is the AV omega, open loop frequency, open loop gain as a function of omega will be at 0 plus 1 plus j omega by omega p. That's a one single pole here. Now, at UGF, at unity gain frequency, I can evaluate AV at UGF, unity gain frequency. So I multiplied by 2 pi ft equal to AV0, 1 plus j 2 pi UGF by 2 pi fp. So it's straightforward. Now, gain at UGF is equal to 1. And if this is equal to 1 here, note that AV0 is a large quantity, 10 to the power 3, 1000, which means that this quantity must be very large as well. Because if this is 1 and the numerator is 1000, which means that this must also be 1000, which means that you can neglect this factor 1 here, and you can show that the pole that you have to introduce is equal to UGF by AV0. First, there's a very simple calculation. So you have to introduce a pole. Whatever UGF you want, the pole that you have to introduce is related to UGF through this expression. So if you want a UG of 10 megahertz, and you know that the open loop gain is 10 to the power 3, which means that the pole frequency is 0.1 megahertz. Okay, so that's the relationship between the pole that you introduce and UGF and the open loop gain here. So, it's a very simple model here. Of course, there are other poles and all that, so which will make this expression approximate here. So now what UGF, as I said, I'm carrying out a very simple design. Actually, the way it should proceed is that you choose a particular phase margin. And from a phase margin, you work backwards and decide where do you want a particular pole, and that pole will then decide how much UGF you are able to get here. So I'm doing it in a simplified way because I don't want to go to phase margin. It's more elaborate. So I'm saying, suppose I use a UGF of 5 megahertz, then the pole required will be at 5 kilohertz. Now, 5 kilohertz, now you have to go and see whether at UGF of 5 megahertz you get adequate phase margin or not. If you don't get it, then you have to choose a UGF of a lesser value. And then you go ahead, choose a pole, and then look at the frequency response and see whether you get an adequate value or not. So you can do a sort of trial and error and figure out what kind of a UGF gives you the required amount of phase margin here. So as I said, I've chosen 5 megahertz. 5 megahertz gives you a pole frequency of 5 kilohertz here. Now, note that every pole that you introduce is nothing but a RC time constant. A simple pole, a single pole can be written as 1 by 2 pi RC. And so what you're looking for is that 1 by 2 pi RC should be equal to 5 kilohertz. For a 5 megahertz UGF with a gain of 10 to the power 3, you require a pole at 5 kilohertz here. Note that if my gain had been higher, say my gain had been 10 to the power 5, then that would have required a pole frequency even lower. And a pole frequency even lower, which means that either the resistance has to be fairly high or the capacitance has to be fairly high here. Okay, so those are the demands on my RC here. So the issue is, how do we introduce the new pole? Where I have my op-amp already, how do I insert a pole into my op-amp here? So the way we do it is, one of the ways of doing it, there are many ways of compensating. So one of the ways of doing it is, we attach a capacitor between this node and this node here. See, we have to introduce a pole, and pole comes about because of an RC circuit. And C, we have to insert somewhere a C here. So we introduce what we call as a compensation capacitor, CC. Now, why do I introduce it in this particular manner? As I said, there are many options. I can introduce a pole, let's say between, at this particular node and ground. I could have taken between here and ground. I could have chosen many places to introduce a pole here. The reason why I'm doing it between these two nodes is, note that the whole op-amp is going to be implemented on chip. And capacitors take up a lot of area. Capacitors take up a lot of area, and you can only build very small values of capacitor. So what we are doing is, we are exploiting the Miller's effect. If you note that what happens is, if I look at, so forget about all the nodes in the circuit for a moment and think about only this particular node here. So at this node, if you think about what is the net resistance at this particular node that you see, RC, because when you look left, you see RC here. And when you look right, you're looking into the base, and then there is a resistor here, and you're looking into input resistance here. Hopefully, you've designed it in such a way that the input resistance of this common collector is much larger. We had said one of the design principle is that this stage should not load this particular stage, meaning input resistance here is much larger than RC here. So when you look at the net resistance at this node, you get RC. Now, time constant or a pole will depend on R, whatever RC is there that you have chosen already, multiplied by the capacitance value. So now you would like to use the smallest possible area to build your capacitance here. And so if I had taken this node and put a capacitor to the ground, then I would have used whatever value of capacitor. Let's say the value comes about to be 100 picofarad. Then I have to implement 100 picofarad between here and here. Now what I do is, I've connected it between these two nodes, and you know that what happens is, this capacitor will get multiplied by the Miller's gain here. Gain between these two stages here. So what happens is, this is a common collector, so gain is 1. The next stage is a gain stage, and therefore the gain is, let's say, 20. So what will happen is that the entire capacitor that you put here will get multiplied by a factor of 20 and appear at this particular node here. And therefore, you can use a capacitor which is 20 times smaller. So that's the advantage of actually connecting a compensation capacitance between these two nodes here. You can use now a much smaller capacitance, but at this particular node, when you look at from here, it will appear as a much larger capacitance. So Miller's capacitance had been bothering us. We were going to common base and common gate and all that to avoid it. But you can see here it is taken advantage of. Here it is taken advantage of to obtain a large capacitor at this particular node, and therefore you can push the pole to a lower frequency. Alright, so the net capacitance that appears is CC, compensation capacitance, multiplied by 1 minus AV3. AV3 is the gain here. Alright, so our choice was, pole was at 5 kilohertz, So what we do is I plug in the values of RC that we had and AV that we had, and from there we obtain a compensation capacitance of 27 picofarad. Okay. You can see here, if you had not used the Miller's effect, you would have required a much larger capacitance. Okay. So the next thing that we do is we go ahead and take our op-amp, and in between these two nodes that you see here, we put this 27 picofarad here. So now we hope that our op-amp has become stable because the pole has been shifted to lower frequency. So when we simulate, note that my UGF goes to about 5.43. We had designed it for 5 megahertz, so it comes out to be 5.43. We know that there are going to be errors, 5.43 and 5.46 megahertz. And our for this value, our phase margin turns out to be 73 degrees here. Okay, so it turns out to be a fairly reasonable value here. Now, as I said, we had chosen rather arbitrarily 5 megahertz. Suppose you had chosen 20 megahertz, right? For 20 megahertz, you go ahead and do the design. Maybe after you do all the design and simulate, you may find that the phase margin is coming to 45 or 40 degrees. So you're not happy with 40. So what you do is you decrease the UGF from 20 megahertz to 10 megahertz, redo the design, and a little bit of iteration will, will allow you to fix the value that you desire here. Okay. So you're taking advantage of a simulator available to you and doing a little bit of trial and error to fix the values of here. So 73 degrees is the phase margin here. So now our op-amp is stable with a good phase margin. So now when I look at, I take my op-amp and I apply the same square wave, as an input, and you can see here the output is also a square wave here. Perfect, no oscillations, nothing there. Okay. So works output is a square wave of 1 volt amplitude here. So all the oscillations have gone. You can take this op-amp, you can build an inverting amplifier, and so you can see the op-amp that is there, and an inverting amplifier is being built. You can see here R1 is 10K, R2 is 100K here, and so 100K, 10K. So we're building an op-amp with a gain of minus 10 and minus 10 here. So you can simulate, and you give a 0.1 volt sinusoid, and you get 1 volt output here. Not exactly 1 volt because the gain of the op-amp is small. Open loop gain is 1000 only. Okay. If it had been 10 to the power 5, you would have obtained an exact 1 volt sinusoid here. So there are small errors because the open loop gain is small here. All right. So let me show you then the. So this is the op-amp that one has designed. Works as expected in simulation. So what one did next was built this op-amp on breadboard. And you guys are going to do 380 and 381 lab next year. So in a 381 lab long back, we had asked students to build this particular op-amp, and so it's a slightly different design here. Slightly some small differences are there. You can see 47 PF because the transistors that we had in the lab were different from the transistor models that we used in the simulation here. So some little bit of tuning and all that is required. So this is the design that was implemented. Okay, so you can see. All right, so this is now. These are all the experimental results. You can see the oscilloscope pictures here. So differential pair in output here. So you can probe this particular point and see the gain of the first stage here. So gain is 19 of the first stage differential pair. This is the input. So we've given an input of 20 millivolt, and this is the output here. And so gain is 19 for the first stage here. This is the final output, open loop. You can see. So what we did was we applied a small input here, and we looked at the overall output here. So we obtained a gain of 1008, very close to what we want here. So you can see. Note the. So you can see here 5 volts is going to 5 volts here, more than 5 volts. It's going to, this is 0 here, so it's going to 10 volts here. You can see plus 10 and almost, this is the ground here. This point is the ground here. So it's going to plus 10 and minus 10 here. So it's able to give you that much swing. But note that no load resistance was connected here. So gain was 1008, and the output, when it was not compensated, the compensation capacitance was not there, then you can see here that it gave all this oscillations in there in this particular op amp here. So one had to compensate in order to get those results that I showed you here. So one built a buffer. You can see a buffer here. So you apply 1 volt. This is the input. You get 1 volt, which is the output here. So buffer works fine, right? So you have your own op amp. You can build your buffer. Now this is a square wave was applied here. You can see square wave here. And what you get is the frequency is on the higher side. You can see the scales are in microsecond here. So what happens is we have not discussed this in this particular course. Op amps in general suffer from a phenomena called slew rate. Slew rate means that when you suddenly switch the input and the input is large in magnitude, what happens is the output, that goes to its final value in a linear manner like this here. Linear manner like this, and it falls linearly like this here. So there is a maximum rate at which the op amp output can change. Maximum rate at which the op amp output can change, and that's called the slew rate here. So this happens when there's a large amplitude input and the frequencies are high, then you start getting this kind of a phenomenon here. So what we can see is a slew rate here. The op amp, you take 741 op amp, you apply an input, you'll also see a slew rate. You'll also see a response like this here. All right, so we made an inverting amplifier. So gain of 10. So this is the input here. That's the output here. So input is I think must be gain of 10 only. So all right. So that's then that brings us to the end of this op amp design. So let me summarize. We had started off by saying that any op amp has 3 at least distinct stages: a differential stage, and in the middle a gain stage, and at the output a stage which is dedicated to providing small output resistance and having a reasonable current driving capability here. So for a bipolar, we had chosen a simple bipolar differential pair. We had chosen a common emitter amplifier, and we had taken a common collector amplifier as a output stage here. And as I just said, the simple differential pair, of course, design is straightforward, but interfacing of common emitter to a NPN common emitter doesn't give us gain, and so we had to take a PNP common emitter stage here. And the other message is that when you're building multi-stage amplifiers, optimizing one stage, for example, we saw that if you just build a differential pair with the maximum possible gain, if you design it like that, then you find that the next stage doesn't have any gain. So you have to look at both the entities together here. It's not that individual optimization will work. In fact, you optimize this, you build a best possible differential pair, and suppose separately you take and build a best possible common emitter amplifier, you put them together, it may turn out to be the worst possible combination. Okay, so that's the general message always there. When you put things together, you have to look at the whole thing. You can't look at it individually here, especially because they are very tightly coupled here. Their bisinks are coupled, and this stage loads the previous stage here, so they're tightly coupled, and therefore you have to look at them together here. And so remember that we had designed this differential pair with the highest possible gain, but it didn't give us, this stage didn't give us gain. So that's why we had to go back and lower the gain of this one, make it deliberately bad so that this stage can improve, but then the overall amplifier improves. Overall gain of the amplifier improves. So we had to do that. And I'm not making any claim that that's the highest value of 1000 is the highest value of gain that you can get. I'm sure if you sit down and optimize it further, you may be able to push the gain further. Okay, so I just gave you a sample design there. The other thing was, then we put a common collector stage here, and we have said it many times that when you use a common collector or a common drain, the best way of biasing is through a current source. If you bias it through a resistor, then the current requirement to achieve a particular kind of swing is very large. If you bias it through a current source, the current requirements become more modest here. And so this is a very simple output stage here. Obviously, this stage doesn't have very good efficiency. We saw that efficiency can be at the most, it's less than 25% or so. And so a better op-amp would have a push-pull stage here. A push-pull stage has to be used in order to achieve a reasonable efficiency. Okay. All right. So in our effort to get higher, lower output traces, we had used this, and I sort of abandoned it and went for this particular stage. But doesn't mean that this cannot work. In fact, if you go ahead and optimize, I have not looked at it, but it's quite possible that you'll be able to get 1000 gain, lower output traces, and input traces through maybe this particular stage here. Not only that, there are various other options. Note that you can use a Darlington stage to lower the output resistance. You could have used this particular one also as a Darlington stage. I can take Q1 and take an amplifier like this here and put it at the input stage here. And then what will happen is you can easily obtain a mega ohm kind of a input resistance. Okay. And so there are various possibilities, but we said that another way of handling the output resistance problem was lowering this resistance here and then compensating it by putting a common collector stage here. And finally, we saw that almost all the op amps that you will build, they will all be unstable. They will all give you negative phase margins, and you'll have to put a compensation. You have to have a compensation strategy here. And this is a very simple compensation called Miller's compensation, which allows you to introduce a dominant pole and thereby obtain a stable amplifier here. All right. So that's the end, I guess. And that's it. Okay. So that's where we stop as far as the course is concerned. And